Good afternoon, everyone. Thanks for having me in this session. Today, I'd like to talk about our recent efforts on seismic detection of voids and tubes within the GEOS team, mainly from a modeling perspective. The surfaces of terrestrial planets of the solar system have been explored using cameras and by rover missions, but very little is known about the subsurface and underground voids. Their presence on the Moon and Mars has been a matter of debate for more than 50 years. The lava tubes are well known in terrestrial volcanic areas, such as the Lava Beds National Monument. They can provide shelters for human habitats, shielded by cosmic radiation and lunar impacts, and also suitable for housing a permanent base with access to several natural resources, including like water, ice, or volatiles. As an important ISRU target, lava beds have been explored. Lava tubes have been explored using multiple geophysical tools, or as analog experiments. They can be identified on GPR radiograms or as magnetic or resistivity anomalies. In this study, we're trying to answer if seismic methods can be used to detect and identify lava tubes and the predicted signatures of lava tubes on seismic images. Let me start with a really simple cave model, which is 10 meters deep and 20 meters wide. The P wave velocity in the cave travels at sound wave speed, and the S wave velocity is 0. The seismic line spans 100 meters with short and receiver spacing is 1 meter. On this short record on the right-hand side, both P and S wave are visible, and the wave pattern outlined in the right box shows the scattering, the back scattering between the free surface and the top of the lava tube. So if we quantify the seismic energy within this window, by grouping the neighboring traces of each shot and calculate the total seismic energy in the time window, we can identify coherent seismic backscattering enhancement within the lateral extent of the cave. In addition to this overall seismic energy, we are also interested in the reflection characteristics of lava tubes. And then we use a more realistic model with an irregular shape. And the background velocity model and the seismic survey geometry is similar to the previous example. And we include the typical reflection seismic processing workflow and the seismic migration approach, which locates the reflector to the actual depth. On the right-hand side, both images show this strong seismic reflection due to the top of the cave. But in most cases, the seismic signals from the floor of the tubes are not visible. In real practice, seismic data sets contain both reflections and diffractions. And based on the low-rank properties of the reflection data matrix and their different kinematics characteristics, we can separate the seismic diffraction from reflections. And the migrated diffraction section on the right-hand side shows a much sharper image compared to the reflection section. It shows a sharp contrast between the overburdened rock and the tube. So all this analysis can be readily extended to a 3D domain. And in this 3D model, we introduced, so the model, the lateral extent is 50 meters, and we introduced the cave 50 meters long, and the background velocity model is similar to our previous example. And the survey geometry, this time is 50 by 50 meters grid with 1 meter receiver spacing. On the final seismic images, both P and S wave reflections are visible, but compared to S wave reflections, P wave reflections are much weaker, and they are strongly interfered by the direct S wave arrivals. Yeah, so this is a P wave reflections, and this is the stronger S wave reflections from the top of the tube. This is along the tube axis, and across the tube axis, we can still see this weak P wave reflection. But on both direct dimensions, they are strongly affected by the direct S wave analysis. This pose challenges for our interpretation of the real field data. So to test our performance or the applicability of our approach to actual field data, so geodes went to Lava Beds National Monument 2 months ago, May 2024, conducted both 2D and 3D seismic experiments near the shape cave. The shape cave, and this is 2D geometry, and we have a 3D geometry, and we're trying to compare with the LiDAR topography. On both 2D and 3D seismic images, similar to the modeling results, we can identify the reflections from the tube ceiling. And in particular, on the 2D profile, we can the shape of the ship cave is clearly observable, shown as the dashed curve. On the 3D images, this is a little bit challenging to interpret because the strong interference from the surrounding bedrock. But we can try to interpret. So this may be this is along the tube axis. So this is the reflection from the tube at the top of the tube, and this is the this across the tube axis, which is the reflection from the top of the tube. So in summary, lava beds produces stronger seismic backscattering energy, mainly from the tube top. And the seismic reflection diffraction presents potential methods for identifying lava beds and the void spaces, including their location and depth, but there's challenges interpreting the actual shape and the size. Future work includes revised processing steps to enhance the seismic signals. And we are also interested in the actual the frequency characteristics of the both reflection and the diffraction. And I want to highlight our methodology can be augmented by including seismic surface waves. So there will be a poster by a GEOS graduate student, Jacob Giles, working on imaging the near-surface structures using seismic surface waves for lunar exploration purposes. And then our approach is really applicable to the analog field data. I have to say our models are simplified, but the automated goal is to build the knowledge base and the framework that can be applied to future lunar missions. That's it. Thank you. I'd like to take any questions.
Time for a quick question.
The wonderful talk. The model and the data you showed were for relatively shallow lava pits. Do you have a sense of how deep you could push the detectability for any deeper structures?
So there's a trade-off. If the tube is too shallow, it's hard to identify from the seismic images because the seismic arrival time is just too short. But it's too deep, and depending on the source you have, you may not have very deep depth penetration to very deep caves. So this model, we use 10 meters as the benchmark test. But we do have models with 6 meters, 10 meters, and even 50 meters. I mean, deeper caves is it's much challenging to resolve.